Okay, everyone. In this video, we're going to continue where we left off in the previous one where we talked about the fundamental theorem of algebra. So we discussed all the major things about the fundamental theorem of algebra. Now we're going to apply that knowledge to kind of answer some of these questions about, some of these graphs that we're going to see. So there's 10 in total. We already did one on the previous video. We're going to do the next 10 here. And I think after doing so many of them, you kind of start to get the basic understanding. But there are some very key things to point out, some very tricky things we got to be aware of. All right, but let's start with this one. Now this function that I see here on my left is an odd function. Not because it looks odd, but because it's odd functions have opposite directions on the end. So it's going down on the left, but it's going up on the right. Both ends are going opposite directions. That's your sign that's an odd function. Remember, even functions would both be going the same direction. Either both of them would be going upwards or downwards. Okay, so an odd function is this one. Positive or negative. Now this is kind of tricky, but it's definitely positive. And it's positive because it's sort of, if you look at it from left to right, it has a trend kind of in upward direction, like a positive linear slope. So kind of the rule of thumb here is it's going to be positive if you're going down on the left and up on the right. Words, man, I have a hard time writing sometimes. Down on the right, and it's going to be negative, or up on the right. Negative if it's the opposite. So -1 would be going up on the left, and that's terrible. Okay, and down on the right. Okay, so that's how you can tell. So this one's going down on the left, up on the right, hence it's positive. Now degree. Now remember, degree, you're sort of making a guess, technically, because it's kind of impossible to say the degree because, we know it's an odd degree, that's a guarantee, but sometimes, we're going to say it's at least a third degree or cubic function just based on the fact that it's got, kind of those two major curves. So we talked about kind of looking at the degree based on the number of curves. Notice that one curve here, kind of like a quadratic, right? Has that U shape, but then it has another curve. And each curve you add is kind of like an additional degree, essentially. So the more curves or the more bends you have in your function, the higher the degree typically. Again, that's not necessarily true every time, but it's a general consensus. It's a general rule. Because it has very few curves, it's definitely, I would say, let's go with degree 3. Now, if it's a degree 3, it's going to have 3 roots in general. Okay, because remember, fundamental theorem of algebra says that the degree of the polynomial corresponds with the number of roots it has. If it's a third degree polynomial, it has 3 roots. If it's a fifth degree polynomial, it has 5 roots, and so on and so forth. So the trick, though, is how many roots are real, how many roots are imaginary. It has 3 in total, but of those 3, how many are real, how many are imaginary? Now, real roots are easy to identify because they're x-intercepts, or essentially they're based on the x-axis. So let's look for those first. Well, I've got one x-intercept, and therefore I've got essentially one real root. I don't have any other real roots, but I have 3 roots in total. Sorry, I've been talking all day. I got 3 roots in total, and one of them's real, which means the other 2 roots must be imaginary. There's kind of a way to see that on the graph, but it's really hard to explain. So what I do personally is just, I know what the total number of roots is, because that's the degree. I know the real number of roots because I can see them on the x-axis. And I'll just take the difference between them, and the difference between them, how many leftovers, how many are imaginary. That's kind of my rule of thumb. So this one we'll practice on this. This function is an even function. And it's even because both the left and right side are going the same direction. They're both going up. And because they're going up, that makes it positive. If both ends were going down, it would be a negative function. So degree, based on how many curves this has, I would say it's degree 4. Remember, you can kind of count the curves. So think of that U as a quadratic. That curve adds a cubic layer. and then another curve would make it fourth degree. Now again, it's not a guarantee that it's fourth degree, but we're gonna, at least a general rule of thumb for algebra 2 is it's probably a fourth degree. Now the total number of roots is always the same as the degree. So if it's a fourth degree, it has 4 roots. So now the question is, how many of those roots of those 4 are real? How many are imaginary? So let's start with the real. Real roots are always on the x-axis. So let's look for those. There's one here, 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 and there. Well, okay, that's, if you count them up, that's 4 real roots. Now there are 4 roots in total. 4 of them are real. That means none of them are imaginary. And we move on to the next one. The next one, even or odd. This is definitely odd. Not because it looks weird, it certainly looks odd, but because one side's going up, the other side's going down. So odd functions do that. They have opposite end behaviors. Now, as a positive or negative, though, if you go back a little bit, you'll see that we mentioned it's positive if the left side's down and the right side's up. But this one, the left side is up and the right side is down, making this negative function. Okay? And again, it's basically because the trend from left to right is it's kind of going downwards, left to right, like a negative slope. All right? Degree, again, based on the number of curves. Now keep in mind, the degree should be an odd number because we just said it was an odd function, so it should be something like a 5 or 7 or 9, but let's count the curves. So let's count this as a quadratic. That's degree of 2, 3, 4, 5. So degree 5, we're going to say, which means it has 5 roots. So we're going to look for x-intercepts. We're going to see how many of them are real, how many are not. If you look on the x-axis, you'll see only 1 root. So it has 5 roots, but only 1 x-intercept, therefore only 1 real root. So there are 5 total roots, and only 1 of those 5 is real. That means the other 4 are imaginary. All right. To move on, this is an odd function. If you guys would like to, kind of pause the video as we get to the next one and try it on your own and then see if you're right, you're certainly welcome to. I highly recommend it. All right, otherwise you can just kind of listen and follow along. The left side is going down, the right side is going up, so this is a positive odd function. Degree, well, it kind of looks like a cubic again based on the minimal number of curves it's got. It means it has 3 roots in total. So let's count how many real roots it has. It's got 1 real root here, 1 here, and 1 here. That's 3 real roots, which means there's no room for imaginary roots. Remember, the total roots should be the sum of the real and imaginary. Of course, 3 roots is equal to 3 plus 0. So our next one, again, if you want to pause it, you can. We'll quickly go over this. Even function or odd function? It's even because both ends are going the same direction. It's positive because both ends are going upwards. The degree, well, it looks like a quadratic. Quadratic's a degree of 2. Total roots, if it's a quadratic, it has 2 roots. Again, these always are the same. Real roots. So real roots, again, you're looking at the x-axis, you're going to look for any x-intercepts. Now, there at no point does my function, my little parabola, cross or touch the x-axis. Not once at all. So that means there are 0 real roots. So if there are 0 real roots, that must mean there are 2 imaginary. At the very end of this video, I'll quickly try to explain how you can see. I mean, you can't really see, but you can look at the graph or signs of where imaginary roots might be, or at least what to look for. I'm not going to explain that now because we can go through this whole thing without having to do that. But if you're interested, watch the end of the video. I'll try to explain sort of my reasoning behind it. It could be, I'm not wrong, but I'm sure there's a more technical way of explaining it than what I'll do. But we'll certainly talk about it, and at least how I recognize it. So this function, even or odd, this one's definitely odd because, again, different directions. Now, this one's actually going to be very interesting. This is positive because it's down on the left and up on the right. Degree. Now, it doesn't really have that many curves. But if you remember, A linear function is just a straight line, so it's definitely not a linear function. A quadratic function is a U shape. It has one turn in it, but it's an even function, and they both go the same way. We already know it's odd, so it has to be like 1, 3, 5, or 7 or something. Can't be quadratic because quadratics would be even. We just mentioned it's an odd. So it's probably a cubic. Now, our example earlier had a cubic looking like this.
May I have your attention, please? This announcement is just for the students that are staying for tutoring, those students only. If you are riding a different bus than usual, please call extension 1000. Those students that are staying for tutoring, if you are riding a different bus, please call extension 1000. Thank you.
That cubic function we saw had so many curves, right? It was pretty obvious. But if you imagine squishing it a little bit, kind of like pushing this side up and pushing this side down, right? And making it smaller, eventually it kind of flattens out and looks like this, which is what we have here. So this is definitely going to be a cubic function of degree of 3. And that's sort of a good visual as to why. So the total roots it has is 3. Of course, it has to be the same as the degree. But how many real roots does it have? How many imaginary roots? This is the trick, because there's only one clear and obvious x-intercept. It doesn't mean that there's only one root. We've talked about multiplicity before, I think in the previous video. And that's definitely the case here. This actually, and I'll just cut to the chase, and I'll try to do my best to explain why, but this has 3 real roots and no imaginary roots. And I promise there's probably a better way of explaining it than what I'm going to do, and I apologize for that, but I'm going to do my best to kind of emphasize my point. So you know how we just mentioned this up here? How it had those bends before? Let's kind of zoom in really closely, all right? I'm just going to draw over this graph, but imagine we're zooming in all the way down here. Okay, I'm going to put that over there. Imagine that, you know, of course it looks like this, where it's got just like one little point there. But imagine, you know, we didn't squish it all the way, you know. We had it like this wave up here, but we didn't squish it all the way. And it was kind of like a little bit up and a little bit down and then up there. So you didn't really flatten them out yet. Of course, if you did that, you would notice, if you count the x-intercepts really close together, you got one here. I'll just do this in a different color. You got one here, there, and there. But if you, the more you push these in, those x-intercepts get closer and closer together until eventually all 3 of them kind of meet in the middle and come together as one. So you basically have 3 points overlapping each other. And so therefore you have those 3 real roots all conjoined at the same point. And what this is it's called multiplicity. Something like this, and this isn't the case on this one because it's all at 0. But imagine you had x minus 3, x minus 3, and x minus 3. All these factors would be x equal to 3, which means there's only one solution or one x-intercept, but there are 3 sources of it, and they all converged at that one point. So they're all roots. There's 3 of them. It's just they're all 3 of them are exactly the same. So you'd have 3 real roots, but they're all the same. So you'd only see it at one point. And that's the case for this one, but this one's at 0 instead of 3. So if you want to imagine this, I guess, as zeros, you can. That's essentially what's going on. Is you have 3 real roots, but all 3 are exactly the same. So you only have one point that you're going to see them. Okay, that's what multiplicity does. It means that there's overlapping points. That's kind of why I drew this picture here. So you can see that all 3 points kind of converge in one, and they start to overlap each other, and they're exactly the same point. But all 3 of them are there. They're just at the same exact place. It's very tricky to know when that's happening, but I always kind of think of it as that zoomed in picture. And I think, well, how many points would be there if it was pulled apart just a little bit? And then when you put it back together, how many points are converging at the same place? So that's kind of the way I think about it.
Research would you call Tiffany Turner? Researcher called Tiffany Turner.
All right, so let's move on to this next one. This also has some multiplicity as well. This function is an even function. It kind of looks silly because some of it got cut off, so I think it's supposed to, let's imagine it looks something like that, where it turns around, but both ends are going down, right? So both ends are going down, both ends are going the same direction, therefore it's even. Now, since it's going down, that makes this function negative. The degree, I'm going to go with degree 4 based on the number of curves it has. So it has a curve here, right? That's 1. Let's go back to blue so you can see it a little better. Has a curve here, like a quadratic, another curve like a cubic, but then another one eventually up there to make it that quartic. So it's got that many curves. We're going to go with 4th degree, which means it has 4 roots. Now, how many roots are real? How many are imaginary? Now, again, this is kind of a tricky one because I see 3 x-intercepts. All right? 3 x-intercepts. But you can't have 3 real roots and 1 imaginary because remember, imaginary roots have to come in pairs. This has to be an even number or a 0. It has to be either 0, 2, or 4 in this case. You can't have just 1 imaginary root. Imaginary roots have to come in pairs. So it can't be 3 and 1. But I definitely only see 3 x-intercepts. And that's because this one here is counting as 2. And that's based on the multiplicity again. So that one counts as 2, then you got the 3rd one, then you have the 4th one. So you have 4 real roots and 0 imaginary. So again, imagine we did that zoom in picture like we did last time. Let's imagine that we zoom in to this right there, right? And of course it only hits the x-intercept once, but like I said, imagine that you stretched it just a little bit. Okay, and it was slightly above it and then slightly past it, right? You would see that it would have 2 x-intercepts. Now, as you bring that line down, as you pull this down, those get closer together until both of those merge in 1. And because you got 2 points merging together as 1, you have 2 points overlapping themselves. Therefore, you've got the multiplicity. You have 2 points here. Okay, you have 2 points, like I said, collapsing together. 2 points in 1. All right, think of it as, to make a root, you have to go past the x-intercept, and then to make another, you'd come back across it, right? Going across it once is 1 root. Going back across it is a 2nd root. Essentially, that's happening at the same time here. You're going across it and back down again at the same place. So you're doing 2 and 1. And I guess you want to think of it back on that last one that we just did. If you think of it, the last one like this, the cubic one, it's kind of going above the function, then below the function, and then above the function again, which is why it had 3 and 1. That was the last problem. But it has to go through all those. It has to make all those cut-throughs, essentially. But it's all happening in the same place, which is why it's an overlap, which is why we called it multiplicity. All right, moving on. Even or odd. This one is an odd function because it's going down on the left and up on the right, so opposite directions. And it's positive because it's going down on the left and up on the right. Should really make words look better. Positive. Degree, definitely a degree of 3. It means it has 3 roots. And very similar to the previous one we looked at. How many real roots does it have? How many imaginary? It has 3 in total. But if you look at the x-intercepts, I see 2 x-intercepts. But again, you can't have 2 real roots and 1 imaginary because imaginaries have to be paired. They have to be either none, or there has to be a pair of them, or there has to be another pair of them, 0, 2, 4. It has to be an even number. You can never just have 1. So we know it can't be 2 and 1, even though that's what it looks like. And again, that's because right here, that point is counting as 2. That's a multiplicity again. Multiplicities are always where the vertexes are. Because the vertex, like I said, think of this line as it's going below it and then back up again, and therefore it's counting as 2. Because when you cross it once, that's a root, but when you cross it again, that's a 2nd root, and that's happening. Those 2 events, going below it and above it, are happening at the same exact time. So you're having those 2 roots happen together. Therefore, that's why it's counting as a double. So vertexes typically will do that. All right. So you have 3 real roots there, even though you really only see 2 obvious. You just have to remember that that's counting as 2. So if that's counting as 2, then this is counting as a third one. So you have 3 real roots and 0 imaginary. All right, so even or odd. This one's even because both of them are going the same direction. It's positive because they're going upwards. Degree. The degree is 4, just based on the number of curves it has. The total roots would also have to be 4. Again, those are always the same. Real roots. So let's look. It's got 2 x-intercepts. And notice, again, there's neither of those are vertexes or vertices, however you want to say it. Right? It crosses it once, and then it comes back up and crosses it again. Those are 2 very independent roots. So there's 2 real roots, and then the other 2 are imaginary. This is an odd function. Right? It's going down on one side and up on the other. It's a positive function because it's going down on the left and up on the right, as opposed to the opposite way. Degree, let's count it. So this would be degree of 2, degree of 3, degree of 4, degree of 5. So 5 roots. So how many of these roots are real, how many are imaginary? So here's one very obvious real because it crosses the x-axis once, right? Has that x-intercept. And doesn't ever come back down again. So there's only one real root, which means the others are all imaginary. That must mean if there's 5 in total, 1's real, then the other 4 are imaginary. Again, I'll kind of illustrate how you can see those. All right, we're gonna quit it there. So that's gonna be it for really the notes part. But if you're interested, I'll try my best to explain how you can see imaginary roots, even though it's really not technically correct, but what kind of gives it away where you would see the imaginary roots. What's kind of here that shows the imaginary roots exist? And it's basically, think of parabolas. Look for parabolas, because we know a parabola like this, right, that never crosses the x-axis, has 2 imaginary roots. So essentially, every time you see a parabola that doesn't cross the x-axis, that's hiding your imaginary roots. So if you look at this one, for example, and that kind of looks like a funny looking smiley face, but you'll see kind of a parabola here. If you look at this, right? That's a parabola. Notice it doesn't ever hit the x-axis. That's hiding 2 imaginary right there. And then there's another parabola right here that's also not touching the x-axis or crossing the x-axis. So that's also hiding 2 imaginary roots. So kind of look for that. Let me go back to some other ones where we saw imaginary roots, and we'll look to see that those parabolas exist but don't cross the x-axis. So look for U-shapes that don't cross the x-axis. And that's not very reliable now that I think about it, but let's see if we can identify it. Okay, now, so this one, I'll try my best to explain this, but there's this parabola here, right, that obviously doesn't hit the x-axis. So there is your 2 imaginary roots showing. Okay. Now, parabolas can be upside down, but here's the reason why you wouldn't, for example, look at this as a parabola. You can't really see this as a parabola because you're sharing this side of it with one that's connected to a root. Like that line has an x-intercept on it. So we're not looking at that side of it. We have to look at lines that go towards the x-axis but never cross it. So we can't look at this side because that line goes towards the x-axis and eventually crosses it. If you're looking at parabolas, quote-unquote parabolas here, you're looking at lines that go towards the x-axis but then never cross it. They turn away from it. So that's why you look at this parabola as opposed to the other one. Because if you looked at this instead, you would see that that parabola would eventually cross the x-axis. So you have to look for ones that are always going away from it. So if you look at like this one, you can't use this. Oops. You can't look at that side as a parabola because that one goes towards the x-axis and eventually crosses it. You have to look at kind of the next curve over. You have to look from here on over. There's a parabola that goes towards the x-axis and then pushes away from it. And then you would see the other one, the x-axis, and then pushes away from it. You can't have them overlap as well. You can't say like that's a third one there. They have to be separate in a sense. So I wish I had like cool animation tool because I could really explain it with a cool animation tool, but I don't have it. But that's sort of a way to spot them. If that's too much, please don't worry about it. It's totally cool to just stick with finding the real roots, understanding if there's multiplicity or not, and then identifying how many imaginary are left. That's my preference. So don't really worry about it too much. Those are just kind of like the signs of how you could see imaginary roots, even though you really can't, okay? At least on these graphs.